Bismillahirrahmanirrahim. This is Pakistan International School Taif, grade 11. So students, we are discussing lecture number 26, chapter number 3, Molecular Orbital Theory, grade 11. So in the last lecture I gave you some introduction about the molecular orbital theory. According to molecular orbital theory, if you listen to my previous lecture, when the two atomic orbitals mix together to form two molecular orbitals, one is called bonding molecular orbital, sigma bond. Other is called anti-bonding molecular orbitals, like this. Sigma star. When two atomic orbitals mix together to form two molecular orbitals, one is called bonding molecular orbitals, less energy and stable, strong sigma bond, and other form anti-bonding molecular orbital, high energy, less stable, weak bond, sigma star. So here are the some rules after doing the molecular orbital theory. All rules of filling orbitals. When you done the electronic configuration, you done the three rules in the previous chapter: Aufbau principle, Pauli's exclusion principle, and Hund's rule. You have to follow. You have to follow these all rules. So two electrons from each of the atom fill lower energy is called bonding molecular orbital, sigma bond or pi bond, and other is a slightly higher energy is called sigma star and pi star. So students, there is a diagram. If you see this diagram, you can see from this example, energy is going to be increased from bottom to top. Suppose you have a hydrogen atom and atomic number is 1 and there is a 1s1 like this one. 1s1 electronic configuration for the hydrogen atom, and that is spherical shape. Spherical. On other hand, you have also another hydrogen atom with the same 1s1 electronic configuration. So according to definition, when these two atomic orbitals mix together to form two molecular orbitals, one is called a bonding molecular orbital, which has less, below this line, less energy. So this is called a bonding molecular orbital. Bonding molecular orbital, which is called a sigma bond and 2s2. One electron from here, one electron from here to give a 2s2. Like bonding molecular orbital, less energy, strong bond, sigma. And other one which is high energy is called anti-bonding molecular orbital, is called sigma star. So like this. Not a perfect overlapping. 2s, no electron, sigma star. Anti-bonding molecular orbital. So anti-bonding molecular orbital may contain the electron, may not be, depending upon the original electrons present in an atom. In the hydrogen, there is a one electron, one s1, other hydrogen atomic orbital. These are atomic orbitals. One atomic orbital, one s1 hydrogen, other atomic orbital, one s1 hydrogen. After mixing, form two molecular orbital. First fill bonding, then fill anti-bonding. So one electron and one to give a 1s2 to form a hydrogen molecule. The bond between hydrogen molecule is a sigma bond, a strong bond, stable bond, has a lower energy bonding molecular orbital. Then according to the theory, according to the definition, another bond which is called anti-bonding molecular orbital. 2s and no electron is there because 2 electrons are contribute here, present. So see the gap, not a perfect overlapping, not a good overlapping, not a good mixing, weak bond as compared to sigma, and high energy, unstable, and is called sigma star bonding. So dear student, this is the definition. When you explain, when you write, when you define the molecular orbital theory definition, and this simple example of hydrogen atom. Okay. Now, the atomic orbitals of the same energy shown in at same level. The difference between energies of atomic orbitals and bonding orbitals depending upon extent of overlapping of atomic orbitals. Large overlapping, perfect overlapping, lower energy, strong bond. Higher energy, poor overlapping, not good overlapping, not good mixing, sigma star anti-bonding. Larger overlapping, stronger will be the resulting bond. According to this one, so you have to remember this energy increasing. You have to fill according to this one. Students, first of all, you have to fill sigma 1s like this. Then you have to fill sigma star 1s. 2s. Sigma 1s, sigma star 1s, then 2s, sigma 2s, then sigma 2px, sigma 2px, then pi 2py, same energy degenerated pi 2pz. Both have the same energy we call degenerated atomic orbitals is equal to then pi star higher energy. pi star 2py is equal to pi star 2pz. And the last one is sigma star 2px. This is the increasing energy of the atomic orbital according to Aufbau's principle, Pauli's experience principle, and Hund's rule. This is going to be general. We follow this, but there is one thing I will tell you. Sigma 1s lowest energy, then sigma star 1s, then sigma 2s, then sigma 2px, then sigma 2py, sigma 2pz, same, both degenerated, then sigma star 2py, then equal to sigma star 2pz, and last highest energy is sigma star 2px. Note it, very important. See, as we done in the previous lectures, sigma bond is formed by the linear overlapping, straight overlapping, end-to-end overlapping between s and s atomic orbitals, s and p atomic orbitals, and p and p atomic orbitals. Sigma bond is going to be formed between these with the head and end-to-end overlapping, linear overlapping. Head-on approach can take place between S and S, S and P already I have mentioned here. When two S atomic orbitals overlap to form two molecular orbitals, this example is given here. Sigma bond is going to be formed here. The two molecular orbitals are going to be formed. One has a higher energy, which is called antibonding, and other is a lower energy, is called bonding molecular orbitals. And students, there is another way we are calling pi bonds. This is called pi bond, and this is between P and P. Because first bond is called sigma bond, 1 electron, 1 electron, 1 electron, 1 electron, 1 electron, 1 electron. If P has more than 1 electron, then first bond, sigma bond, and other is called pi bond. So pi bond is formed by the sideways approach, parallel overlapping. So when the axis of two p orbitals, py, pz, are parallel to each other, they interact to form molecular orbitals. The bonding molecular orbitals py and pz has a zero electron density. The nuclear axis called nodal plane, already I told you. The electron density is uniformly distributed above and below the nodal plane. This is the nodal plane, I told you, like this one. This one. This is the nodal plane. Here electron density more. Above and below, like this one. So, on the other hand, we have antibonding, pi star to py and pi star to pz, unstable, weak antibonding. Has electron density in the internuclear region. Since 2py and 2pz atomic orbitals are degenerated, having the same energy, so we write in the same line. These are degenerated. Pi star to py, pi star to pz, and pi to py and pi to pz. These are equal energy degenerated atomic orbitals. Yes, pi molecular orbitals, pi to py, are also degenerated. Pi to pz also degenerated. So the two set of 2p orbitals, two set. This is the one set and this is the other set. This is the one set, this is the other set. 6 molecular orbitals, 3 bonding and 3 anti-bonding. Means sigma bond and sigma star one pair, pi and pi y and pi z is the second pair, pi star y, pi star 2p, they are the third pair. 6 total. The bond formed as a resulting of linear overlapping sigma bond, parallel overlapping pi bond. Yes. This is the one thing. In the previous lecture, I told you molecular orbital theory is superior to both Vesper and valence bond theory. The first thing I told you, paramagnetic nature is explained by MO theory. And second is bond order. Bond order, single bond, double bond, triple bond. What type of bond is formed is called bond order. No bond maybe. The formula of bond order is, if you see your book, number of electrons in bonding molecular orbitals, number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbital divided by 2. This is the formula. You can calculate the bond order. Number of electrons downward bonding molecular orbitals minus number of electrons above the line is called anti-bonding molecular orbitals. Put in this formula, divide by 2, you will get the bond order. Suppose in hydrogen, if you have 2 electrons in bonding molecular orbitals and no electrons in anti-bonding molecular orbitals, 2 minus 0, you will get 2, 2 divided by 2. So the bond order of hydrogen molecule is 1. Okay. It's common practice that NO molecular orbitals formed from the valence orbital are considered in bond order calculations. It should be noted that bond between 2 atoms can be formed only when the number of electrons in bonding orbital must be greater than that of number of electrons in anti-bonding. So if this number is greater than this, you will get a bond. But if this number is equal, you will get 0. If number is less than this, you will get again no negative bond order. If there is a bond formation 1, 2, 3, bonding molecular orbital electron must be greater than that of the anti-bonding molecular electrons. Students, this topic which is a very important and many times it is asked in the board paper. Many times. So write down. Relative energies of the molecular orbitals. According to the spectroscopic studies, the relative energies of the molecular orbitals formed from the 2s and 2p atomic orbitals are determined by the spectroscopic measurement, 2s and 2p. Very important. When students, these diatomic molecules, oxygen, fluorine, maybe boron, see boron is maybe, and their positive and negative ions, positive and negative ions. So order of increasing their energy is as follows. Sigma 1s already I draw in the previous, yes, you can see this is same 100%. Sigma 1s greater than, this is less than this, that is sigma star 1s. Then sigma 2s. Then sigma star 2s. Then pi 2p y is equal to pi 2p z greater than pi star 2p y is equal to pi star 2p z, and the last is a sigma star 2p x, as I had done before. So students, when you have these examples, oxygen, if you want to draw the structure of oxygen, fluorine, boron, which I will explain later, and the positive and negative ions, you have to follow this increasing order of their energies. Increasing order of their energy, you have to follow this. Sigma 1s, then sigma star 1s, then sigma 2s, then sigma star 2s, then pi 2py is equal to pi 2pz same, then pi star 2py, pi star 2pz, and last one is sigma star 2px. This is for the oxygen molecule, fluorine molecule, and also boron molecule. Then, if you are going to explain more number of electrons when you are going to distribute, so hydrogen, helium molecule, not boron, boron molecule, carbon molecule, nitrogen molecule. Especially nitrogen is given in your book, oxygen is given in your book, fluorine also. Yes. So if you are distributing electrons according to this order, so if hydrogen, helium, boron, carbon and nitrogen molecules, so the increasing energy is in this form, sigma 1s, same, no difference. Sigma star, again same, no difference. Sigma 2s, again no difference. Sigma star 2s, same, no difference. Up to here, same. You will find same here, but now in this case, pi to py and pi to p, there's I think one left right there. After sigma star 2s, then there is a sigma 2px. If you start greater than this is less than sigma star 2s then this is, you have to put here sigma 2px, then less than pi to py and pi to pz. Here. Now there is a change. There is a change in sequence in these cases. Means after sigma star 2s, don't shift electron in the sigma 2px, but you have to shift electron pi 2py is equal to pi 2pz. Then you have to fill the sigma 2px. Then pi star 2py is equal to pi star 2pz, then sigma star 2px. So students, I'm going to write this again because this is very important. Maybe you confused from here, so that's why I'm going to write again. So after here same sequence, if match sigma 1s, okay, sigma 1s, then less than sigma star 1s, okay, sigma 1s stars, then sigma 2s, then sigma 2s, okay, then sigma star 2s, sigma star 2s. So here is going to be changed. In case of oxygen fluorine, then you have to fill sigma 2px. There's the difference. See this one. There's the difference. Then pi 2py is equal to pi 2pz, and pi star 2py is equal to pi star 2pz, and the last sigma star 2px last. So difference is only here. After filling sigma star 2s, in case of oxygen fluorine, fill sigma 2px, then pi 2py, pi 2pz. But in the case of hydrogen molecule, helium, boron molecule, carbon molecule and nitrogen molecule, so this is a difference. Don't fill sigma 2px, direct fill 2py and 2pz, then sigma 2px. So this is the difference you have to write here in your book. This is also written. So students, what is the reason behind? So I will explain in the inshallah next lecture. So this is very important, and many times this question asked in the examination that why in the case of oxygen molecule, fluorine molecule, you are filling as usual according to the three rules, sigma 2px and sigma 2py and 2pz. And in the case of helium, hydrogen, this nitrogen which is given in your book, if you see that sigma 2px here now. First you have to fill pi 2py and pi 2pz, then you have to fill the 2p, sigma 2px. So here the reason is given, explanation is given. So inshallah in the next lecture I will explain this reason. So we are continuing chapter number 3. Thank you very much.